Okay, so we'll start our class. As I said, we are dealing with an Nyquist plot. Okay, so I'm using a notes which I have prepared for explaining the Nyquist stability criteria. So after that, we can solve one problem using a PPT. Okay. So before, rather than explaining you only but theoretical based, I have drawn few examples of a Nyquist plots so that you will get a better idea. Okay. So first Nyquist plot which I have drawn is, see, this is a S plane. Okay. This plane is S plane. This is f of S plane. Okay. So the function f of s is 1 by s square minus 4s plus 8. So if you redraw in terms of poles and zeros plot, so it consists of a two poles. One pole is located at minus 2 plus j2. Another pole is located at minus 2 minus j2. Okay. So what Nyquist plots is there? You indicate these two poles in S plane and take a contour such that it is enclosing these two poles. Now, if I take a clockwise contour, it will enclose entire right hand side to the direction, right? So these two poles are being enclosed. Now, if at all I'll shift, okay, each and every point of a contour on f of s plane, it will result into a, okay, encirclement of origin two times in anti-clockwise direction. So what I mean to say is that conclusion, if your contour in S plane is enclosing two poles, I can observe that, okay, in f of S plane, my origin, that is 0 plus j0 number, is being encircled two times in anti-clockwise direction. So if at all my contour encloses or encircles three poles, okay, then how many times it is going to encircle the origin? It is going to encircle the origin three times. All the three times it is encircling in anti-clockwise direction. So number of anti-clockwise directions in f of s plane is equal to number of poles enclosed in a s plane. Okay. Let us take a second transfer function where it consists of f of s is equal to s minus 1 by s minus 2 by s minus 4. So if at all I'll draw the poles and zeros of this S plane, one zero is located at S is equal to minus 1. One pole is located at S is equal to minus 2, sorry, plus 2, S is equal to 1, S is equal to 2, S is equal to 4. So zeros are S is equal to 1, poles are S is equal to 2, comma 4. Okay. So this is 1, 2, and this is 4. Now I'll take a contour which, okay, encircles all the three roots of the equation, or else we can say it encircles both zeros and poles. Sorry, zeros and poles. So how many poles are there? Two poles are there. How many zeros are there? One zeros is there. So pole is greater than 0. So 2 minus 1, 1. So resultant contour in f of s plane is, it will encircle, okay, the origin one time. It encircle the origin by n is equal to p minus z one time. In which direction? Anti-clockwise direction. Anti-clockwise direction. So what we can conclude is that if at all, okay, there is one more pole here, how will be my contour? My contour is going to encircle two times. Encircle two times in anti-clockwise direction, because 3 minus 1, that is two times. If there is one more pole, so it may encircle three times. So number of encirclements depends upon number of encirclements of poles and zeros in a plane. For example, there are two poles, two zeros. How will be the encirclement? There are two poles, two zeros. If you are encircling two poles and two zeros, that means there are 2 poles and 2 zeros, then it is not going to encircle origin, or it is encircling origin 0 times. Why 0 times? N minus P is equal to 0. 2 minus 2 is equal to 0. If, for example, there exists a 0. So 3 zeros, 2 poles. Then you can see encirclement of origin not in anti-clockwise direction but is in clockwise directions. So number of clockwise direction encirclements is equal to number of zeros. Number of anti-clockwise encirclements is equal to number of poles. Okay, when both are 0, encirclements is equal to 0. Let us take this example. Here it is enclosing uh, 2 poles and sorry, 1 pole, 2 zeros. So P is equal to 1, Z is equal to 2. So N is equal to 1 minus 2. Minus 1 means it has to encircle the origin with 1 time in clockwise direction. Okay. If you are clear, okay. If you are clear, you should able to, for example, if you are clear with the concept, for example, there are 3 poles in S plane. What will be the corresponding in f of s plane? In f of s plane, as number of poles encircling is 3, so you'll get 3 encirclements. All 3 encirclements in anti-clockwise direction. So, if at all there is 2 zeros, then number of encirclement in anti-clockwise direction is only 1 time. Okay, so like that you should able to draw. For example, this is your contour in S plane. What is corresponding f of S plane? So it is enclosing only 1 zero. So one encirclement in clockwise direction. Clear? One encirclement in clockwise direction. Okay. So having got an idea about what will happen if at all you're drawing a counter which is enclosing a poles and zeros to the f of s plane, I will now explain about Nyquist stability criteria. Here also I am taking one example and explaining the Nyquist stability criteria. If you follow any textbook, he will take a pole zero plot and try to explain it. Okay, so I feel that is a little tricky or difficult to understand. So let me take one unity feedback system whose g of s into h of s is given by 10 by s plus 2 into s plus 4. What is the aim of Nyquist stability criteria is to estimate the stability of a system when it is becoming a closed loop control system. That means, what is my closed loop control system? This is g of s. Okay, I know only closed loop transfer function. I have to estimate the stability of a closed loop system. So what exactly we are doing? We are estimating the stability of a closed loop control system based upon data available of only open loop control system. Only open loop control system. I hope you got an idea. Okay. Now we will see what is my f of s, how I can draw the Nyquist stability criteria. So rather than taking a generalized statement, let me take a particular one. That is g of s into h of s is equal to 10 by s plus 2 by s plus 4. If it is an open loop system, the number of zeros are 0. Number of poles are located are 2. One pole is located at minus 2. One pole is located at minus 4. If you plot this open loop poles, there is one pole located at here, one pole located at minus 4 and one pole located at minus 2. System is stable system. But what I have to estimate, if at all I'll convert this open loop system into closed loop system, whether still it will remain stable or these poles may go on to right hand side of S plane. So for that, what we'll do is that first I will try to find out, because a closed loop control system standard transfer function is g of s by 1 plus g of s into h of s. Now, what is 1 plus g of s into h of s? That is my characteristic equation. So, the closed loop control system stability depends upon number of roots of characteristic equation lying on the right hand side of S plane. This we have already done it. Where we have done it? In Routh-Hurwitz stability criteria. In Routh-Hurwitz stability criteria, what we'll do? First, we will take 1 plus g of s into h of s is equal to 0. It will result into one polynomial equation. Then we will take the coefficients of a polynomial equation, we'll draw Routh array and we'll try to find out number of sign changes. So whatever we know, we are in using this or inferring this. So what I mean to say is that the closed loop control system stability depends upon the characteristic equation. If you solve this characteristic equation, fifth order or 10th order, okay, then any one of the roots of the characteristic equation lying on the right hand side of a plane system is unstable. So I'll define this characteristic equation itself as a f of s. So what is my f of s? F of s is characteristic equation 1 plus g of s into h of s. So I'm just doing 1 plus g of s into h of s. Then s plus 2 into s plus 4 is a LCM. Then s plus 2 into s plus 4. Okay, we'll get to numerator plus 10. Now I can simplify it. After simplification, what I will get is s minus 3 plus j3 into s minus 3 minus j3. How I got is I have taken this s square 6s plus 18. So I have not done any calci or any solution. I have used the MATLAB, just define the polynomial equation and take a roots of the equation, or else use your Python programming language, open your Jupyter notebook, okay, define the polynomial function and then just square roots, enter the quotients and then use the roots command, you will get roots of a function. Okay, I got these two roots. Now if you carefully observe, okay, what is numerator? Zeros. What is denominator? Poles. I can say the poles of f of s is equal to open loop poles. What are the poles of f of s? S is equal to minus 2, s is equal to minus 4. I will say the zeros of f of s is equal to poles of closed loop transfer function. Zeros, what are the zeros of f of s? S is equal to minus 3 plus j3. S is equal to minus 3 minus j3. So minus will become plus, right? Plus 3 plus j3, 3 minus j3. Whether my assumption is correct or not, to verify, I'll create a closed loop transfer function. What is closed loop transfer function? G of s by 1 plus g of s into h of s. What is g of s? 10 by s plus 2 into s plus 4 by 1 plus g of s into h of s. As I said, it is a unity feedback system. Okay, now I'll take a LCM. After that, this will get cancelled. Finally, you'll get 10 by s square plus 6s plus 18. I think so. Here I have written wrong. 18, right? 8 plus 10, 18. So if you find out the roots of this equation, it is s minus 3 plus j3, s minus 3 minus j3. What are the zeros of this closed loop transfer function? No zeros. What are the poles of this closed loop transfer function? There are two poles. One is located at plus 3 minus j3. Another is plus 3 plus j3. So whether the poles of a closed loop transfer function is equal to zeros of f of s or not. So I can conclude that zeros of f of s are equal to poles of closed loop transfer function. Rather than analyzing where these poles of f of s is going after creating feedback, I analyze what is the status of zeros of f of s. Okay, if all the zeros of f of s are lying left hand side of s plane, obviously closed loop transfer function poles are also lying left hand side of s plane, then system is stable. So in order to determine this, whether the zeros of f of s are lying on the left hand side of the s plane or not, what we have to do is that we have to take a contour so that it will enclose us all the poles and zeros lying on the right hand side of the s plane. So what is my Nyquist stability criteria is we are going to estimate closed loop control system stability based upon f of s. So what is f of s? F of s is a function which is given by half of the characteristic equation. What is characteristic equation? Equal to 0 characteristic equation. You remove that zeros. If no zeros of the f of s are lying right hand side of s plane, I can conclude that no closed loop poles are lying on the right hand side of s plane. System is stable. Okay. Previously, we have observed certain plots, right? How we can see in f of s, if there is any pole lying on the right hand of the s plane, then you will have a one anti-clockwise encirclement. Any zero lying on the right hand side of s plane, and you draw the contour such that it is encircling that, you will have one encirclement in clockwise direction. If number of poles and zeros are zero, so equal, number of encirclements is equal to zero. If that condition is not satisfied, system is unstable. Condition is satisfied, system is stable. So what we will do is that first select a contour which encloses all poles and zeros on the right hand side of S plane. For this contour, draw the corresponding contour in f of S plane. Now measure how many times it is encircling the origin, whether it is in clockwise direction or anti-clockwise direction. Let P is equal to number of poles, Z is equal to number of zeros. If N is equal to P minus Z, for a stable system, okay, number of encirclements is equal to number of roots lying on the right hand side of the S plane. Okay, zeros of f of s should not lie right hand side of the s plane for the system to be stable. So z is equal to 0. Then n is equal to p. N is equal to p. So what I can say, if zeros of f of s are not lying on the right hand side of s plane, number of encirclements should be 0. So number of open loop poles lying on the right hand side of the S plane is equal to number of encirclements in anti-clockwise direction. Number of open loop zeros lying on the right hand side of the S plane is equal to number of encirclements in clockwise direction. Okay. So this is the way we are going to establish principle of argument, and we can define a Nyquist stability criteria. Once again, why we need to draw complete f of s. What is f of s? It is a function. It is a dependent variable. It depends upon some other variables. So I can rewrite the function as f of s is equal to 1 plus g of s into h of s. Then g of s into h of s is f of s minus 1. How, if at all, how you will get, f of s, right? F of x. For example, f of x is like this. How you will plot f of x minus 1? How you will plot f of x minus 1? For each and every point, I will reduce minus 1. And I will draw the plot, right? So what I will do is that instead of plotting f of s, I'll try to plot g of s into h of s. In g of s into h of s plane. So what f of s will encircle? F of s will encircle origin. So if f of s is encircling origin, if you make f of s minus 1, it will get shifted to minus 1. Okay. So how to get a f of s minus 1? For example, my shape is something like this. F of s. I want f of s minus 1. So at each and every point, I have to take minus 1. Okay, for example, this is my new f of s. So red one is f of s minus 1. Black one is f of s function. If f of s is encircling 0, this will encircle minus 1 plus j0, or in simple minus 1. So rather than checking for number of encirclements of origin, I will check number of encirclements of minus 1 plus j0. Okay, I'll find number of encirclements of minus 1 plus j0. Number of encirclements of minus 1 plus j0 should be equal to number of open loop poles lying on the right hand side of the S plane. Number of open loop poles lying on the right hand side of the S plane. Then system is stable. If it is not matching, system is unstable. Okay. So what we have to do is that to investigate the presence of poles of g of s into h of s on the right hand side, we have to select a contour such that it will cover all the poles and zeros on the right hand side of the S plane. Very simple thing is that, okay, or what I will do is that I'll take my compass with infinite radius, I'll draw the arc such that it will cover entire right hand side of the S plane. So how I can cover entire right hand side of the S plane? Okay, take the length of imaginary axis at plus infinity and start drawing the arc with infinity radius. Okay, and complete the length up to origin. So this arc or this contour is uh, enclosing entire right hand side of the S plane. So whatever might be the zeros or poles present on RHS, it will be enclosed by this contour. It will be enclosed by this contour. So how to find out how many poles and zeros are lying on the right hand side of S plane is select a contour such that it will, okay, cover all the poles and zeros lying on the right hand side of S plane. How to draw that contour? First draw a straight line from origin to plus infinity along j omega axis. Okay, what is C1? Infinite line along a positive imaginary axis. From there, you draw the arc with infinity radius, okay, from plus infinity to minus j infinity. What is C2? It is the arc of radius of infinity, which will enclose entire right hand side of S plane. Then draw a line from minus j infinity to 0. Draw a infinite line along with negative imaginary axis. So a contour consists of three different shapes because I cannot mathematically explain all the three shapes with one equation. So I am dividing that into three equations. C1 is a straight line passing from 0 to plus infinity. C2 is an arc with infinite radius. Okay, from plus 90 degrees to minus 90 degrees. C3 is the line starting from minus j infinity to 0. So what is C1? S is equal to j infinity, where omega varies from 0 to plus infinity. What is C3? S is equal to plus j omega, okay, where omega varies from minus infinity to 0. What is C2? C2 is a arc. Limit R tends to infinity. R tends to infinity. R into e power j theta. R into e power j theta. Okay. This is representing a polar form. Okay. Where theta varies from plus pi by 2 to minus pi by 2. So plus pi by 2, you'll get a here. After that, it will move like this. If you keep on changing this, okay, I mean to say phasor will be changing and it will reach. So your phasor is having a uniform magnitude of infinite radius and angle will be changing from plus 90 degrees to minus 90 degrees. Now what I will do is that in order to obtain the Nyquist plot, okay, I will take C1, draw corresponding C of S into, corresponding G of S into H of S in G of S into H of S plane. What is G of S into H of S plane is nothing but polar plot. For variation of omega 0 to plus infinity along with imaginary axis, I'll draw corresponding polar plot. Then I'll draw corresponding polar plot for C2 and I'll draw corresponding polar plot for C3. If you join all these things, you will get final Nyquist plot. What is Nyquist plot? The plot of G of S into H of S transfer function in G of S into H of S plane. G of S into H of S plane. Okay, after drawing the Nyquist, I will search for number of encirclements of minus plus J0. Whether there are encirclements, if there are no encirclements, I will check whether there are any open loop whether they are any open loop zeros are lying on the right hand side or not. No zeros are lying on the right hand side, then we'll say stable. If there is one zero lying on the right hand side of the S plane, we should see corresponding clockwise direction. If there is any pole lying on the right hand side of the S plane, corresponding encirclement should be anti-clockwise direction. Okay, anti-clockwise direction as many times as number of open loop poles lying on the right hand side of S plane. Now this may be valid, okay, this will be valid for a transfer function of type 0. For a type 0 system, this will be valid. If it is a type 1 system, we will have one pole at origin. So this is not on the right hand side of S plane. Exactly it is lying on the S plane. Then I cannot take a contour like this. I have to reframe my contour or redraw my contour. So it will consist of C1, okay, from plus 0 to plus infinity to minus infinity of R radius arc, minus infinity to 0 minus. What is 0 minus 0 plus? Just after the closing switch, just after opening the switch. That means 0.00001 minus 0.00001. So this is called C4. C4 can be expressed as C4 is equal to limit R tends to 0. It is very small radius, very small radius. Okay, R e power j theta, where theta varies from minus pi by 2 to plus pi by 2. Minus pi by 2 to plus pi by 2. If there are multiple poles lying on the imaginary axis, you cannot take into consideration as the contour. You have to omit all the poles which are lying on the imaginary axis. Then this is C1, then C2, C3, C4, C5, C6, C7, C8, like that. Wherever you are trying a arc to just omit a pole on origin, then it is limit R tends to 0, R e power j theta. Okay, so here the theta may not be exactly always minus 90 to plus 90. It is going to vary it. Okay, it is going to vary it. Okay, so like that, depending upon the pole 0 plot, okay, in S plane, we have to take a respect to contour. So what is the first step in drawing the Nyquist plot is, given a transfer function g of s into h of s or open loop transfer function, for example s plus 2, s into s plus s minus 3. First step is draw the pole 0 plot in S plane. So S is equal to minus 2, S one pole, and S is equal to minus 3. So this is 0. Now what contour I should take? I should select a contour like this. C1, C2, C3, C4. It is covering all the poles on the right hand side of the S plane. Okay, clear? Okay, it may have anything now. You may have another S plus S minus 5 or S minus 10. How many poles are zeros? Now what we'll do is that we'll plot corresponding of C1, C2, C3, C4 in G of S into H of S plane. Then it is going to result into a Nyquist plot. So finally some Nyquist plots may have something like this. Okay, sorry, something like this. Some Nyquist plots may get shape like this. Some Nyquist plots may get shape like this. So first you have to identify minus 1 plus j0. And after that you have to see number of encirclements. So number of encirclements is equal to number of, okay, poles of S plane lying on the right hand side of the S plane. Okay, if that is satisfied, system is stable system. Okay. Anyhow, I'll share these notes for you so that you can understand basic concept of a Nyquist plot. I'll show an example. This is for just analysis. Okay. So how to draw it, I'll explain in my own steps. Okay. So you can take one simple transfer function. G of s into h of s is k by 1 plus st. So what is the type of this system? The type of the system is 1. Order of the system is 2. Okay. So first, if at all you draw these poles and zeros on a S plane, there is one pole at s is equal to 0, another pole at minus 1 by t, another pole at minus 1 by t. So obviously it is here minus 1 by t. Now which contour I should take to analyze Nyquist stability criteria? Second shape of the contour I should take. So first this is C1, then this is C2, C3, C4. So what is C1? C1 is a line going from 0 plus to plus infinity. So substitute S is equal to j omega. If there is a k, we have to take into consideration k also. Okay. So what we have to do is that we have to only consider a straight line. Okay. Which is going from 0 plus to plus infinity. Substitute in this, draw the corresponding plot in g of s into h of s. Okay. So you got a basic idea. So let me see. So we need to draw the polar plot. First, omega is equal to 0. If you place omega is equal to 0 plus, I will indicate like this. Omega is equal to 0 plus. So S is equal to j omega. When you make omega is equal to 0 plus, S is equal to 0. Just substitute S is equal to 0. It will become K. Okay. The magnitude will become K. Right? When S is equal to 0 plus, uh, K, yeah, there is a 0 here. So because of K by S, magnitude will become infinity and phase angle will become, uh, what is the complete phase angle for this? 1 by S will contribute as minus 90 degrees, minus of tan inverse of uh, omega t by 1. Okay. So total theta is equal to minus 90 degrees minus tan inverse of 0. That is minus 90 degrees. Minus 90 degrees. So it is infinity at minus 90 degrees. How you can plot that? That is plus infinity. Okay. Plus infinity at minus 90 degrees. So some point. Okay. Let this is plus infinity at minus 90 degrees. Okay. Now, slowly when omega is equal to infinity, what will happen? K by infinity into infinity plus 1. So this will be 0. This will be 0. Okay. So, and angle is equal to minus 90 degrees minus tan inverse of infinity. What is tan inverse of infinity? Tan inverse of infinity. Is it 0 or 90 degrees? Tan inverse of infinity is 90 degrees, right? Minus tan inverse of 90 degrees. So minus 90 degrees. Okay. Minus 90 degrees. Tan inverse of plus infinity is, so it is going from 0 to plus infinity, right? So it is minus 180 degrees. Or else forget about everything. Okay. So what is the type of the system? Type of the system. The type of the system is S is equal to 0. That is, there is one pole lying on the origin. Okay. So type 1 system. So your plot will start from here. Okay. Order is 2. Okay. So this is type 0, type 1, type 2, type 3. You write down like that. Okay. This is order 1. This is order 2. This is order 3 ending. This is order 4 ending. So it is a type 1, order 2, type 1 and order 2. So my shape will become something like this. Okay. My shape will be something like this. So I no need to do everything with 0 minus. It will be quite mirror image to that. Okay. My mirror image to this means it will be like this. This is plot is for C1. This plot is for C3. This plot is for C3. I will see about other plots. Okay. I'll explain about other plots. I hope you got the value for C1. Okay. For C1, we can draw the polar plot. Okay. And then at plus infinity, as I said, 0 at an angle of minus 180. I have explained it. Okay. So separate real parts and imaginary parts. There is no intersection. Finally, you draw the polar plot. Simple. We can explain everything, or in simple, because we studied about this, we can draw the polar plot for C1. Okay, as I said, C1 and C2 are mirror image because we are plotting a line from 0 to plus infinity. Obviously, when you are plotting from minus infinity to 0 minus, you will get the same, but mirror image of this one. Okay, no need to waste any time on calculation part of C1, C2, C1, C2, C3. Yeah, C3. C3 is this one. C3 mapping is this one. C1 mapping is this one. Now let us see how to map a arc of radius limit r tends to infinity r into e power j theta. R into e power j theta. Okay. So that is all the explanation. You want to use a software, then you can keep on entering the values. You will get, once you write a program, you can keep on entering the values. You will get a corresponding values. Okay. Next, what we have to plot is we have to plot r tends to infinity. R tends to infinity. So this plot is over. We have to plot r tends to infinity. I think I forgot to include that slide. Yeah. And limit r tends to infinity r e power j theta. Okay. So first, when it is theta is equal to plus 90 degrees, plus 90 degrees, right? Theta is equal to plus 90 degrees. And then as limit r tends to infinity, what is the value of magnitude? One by s. Okay. 1 by s into r. Subtracted the imaginary parts. It is an example with values. I can show you better. Okay. But it is 1 by s into 1 plus st. Okay. 1 plus st e power j theta. Okay. So e power j theta is e power plus 90 degrees. If you make 1 by r, when r tends to infinity, okay, when r tends to infinity, you are taking s is equal to plus j infinity to s is equal to minus j infinity. Sj infinity to minus j infinity. So what it will do is that it will result into a arc. It will result into arc of, okay. So starting from, you take this as origin, it is going to result into an arc of r tends to 0, r tends to 0, going from, so it is small dot, we can say it as a dot, or else you want exactly what is going to happen is that as this has been expanded, as this has been expanded, okay. So what exactly it is going to do is that I'll draw the exact plot. This will come like this, okay. And this big circle, big arc will get converted into small arc because it is 1 by s term. Small arc from minus 90 degrees to plus 90 degrees, okay. And then this is going to go into this, and this small r tends to 0. When r tends to 0, this will tends to infinity, right? It will change from plus 90 degrees to minus 90 degrees. Okay. So rather than representing this small arc, we can represent with a dot. Okay. And then this is r tends to infinity. R tends to infinity. So now after drawing the Nyquist plot, number of times it is encircling minus 1 plus j0 we have to find. Okay. It all depends upon when you take a values. Okay. Obviously minus 1 plus j0 it will never get encircled by this. So number of encirclements is equal to 0. So as per my circuit open loop transfer function, there are no open loop poles lying on the right hand side of the S plane. So number of encirclements is equal to 0. Ensure that system is completely stable system. Okay. System is completely stable system. So as minus 1 plus j0 is not encircled by the part, and the poles of g of s into h of s is 0. Therefore, number of roots of characteristic equation with positive real parts is 0. That also you can check it. So number of encirclements is 0. And the system is stable system. So next class I will do 2 to 3 or also 1 or 2 problems on complete Nyquist plot, how to draw it. Thereby we can end the Nyquist plot. Then we can go for a state variable analysis. Yeah. I know it's not easy. Only the Nyquist plot is a difficult plot in complete plots, and MN circles are there. Okay, but once you understand, then you can understand better. Okay, try to summarize it and explain. Try to understand how to draw the Nyquist plot and some logic so that you can answer the MCQs related to that. Okay. So hope so. I'm making hope all 59 students have entered their enrollment numbers in a chat box, right? Okay. Thank you.